Clear things that have to be delineated about Newton's laws before we really talk about problem solving. But I want you to know from the very start that there are problems that are impossible to solve using Newton's laws. Just impossible. So be aware that although you might think, I can always solve a problem with Newton's laws, I can always resort to Newton's laws, that's not actually true. When it comes to Newton's laws, we need a couple of things in order to be able to use them appropriately. And the first is we need constant forces. If the forces aren't constant, it's very unlikely you'll be able to use Newton's laws to solve your problem. And since in this room, everybody's had a course in physics, based on what you see here, would this be, even with friction, would this be a constant set of forces acting on the object? Sure, the ramp is constant, the normal force is going to be constant. Unless you add something tricky, this is probably going to be a problem that can be solved. Now, all I have to do to make it something that is outside of our ability to solve is change the ramp. If the ramp is curved in some way, the forces are no longer constant. None of them are. The frictional force changes, the normal force changes, the component of the force down the ramp changes. It's an impossible problem to solve using Newton's laws. I mean, if the height is the same, the change in energy is the same. Energy might be a better way to solve this problem. But forces work best if you can identify or deal with constant forces. Now, there is an exception, and the exception isn't obvious either. If we can't get constant forces, then we need expressions for forces. So again, if we can't have constant forces, then we need expressions for forces. And if you don't understand what I mean by that, then think back to this lab. All right, the coffee filter lab. There were two forces acting on the coffee filter. There was the drag force upwards and the weight acting downwards. Without too much detail in Newton's laws, weight acting downwards minus the drag force upwards would give us the acceleration of the system. This requires knowing a little bit of Newton's laws, so I know I'm reaching into the future. The reason I say expressions is weight's a constant, it's mg. Drag is proportional to the velocity. This at least gives us an expression for the force. We can use expressions for force if they're not constant. All in all, the only thing Newton's laws can do is tell us an individual force, or tell us the acceleration. That's it. That's all Newton's laws can do. Now, telling an individual force may or may not be particularly useful. Telling us acceleration gives us velocity and gives us displacement. So we know getting the acceleration tells us quite a bit about what the system might be doing. Now, we talked about Newton, we talked about the fundamental forces. Those are all well and good, but let's talk specifically about Newton's laws. Now, there's a lot of ways to go about this. And I don't want to mince words here. I look at Newton's laws as specifically a framework. To me, they're a framework for solving problems. That's not how Newton saw it. Newton saw this as a telltale sign of the way the universe works. If you notice something accelerating, something must be causing that acceleration. He used this as a way of predicting that there were forces that were acting without contact. He was trying to build more than just a framework. He was trying to build an overall theory for the way in which the universe worked. He was attempting to prove something to people. We're not. We're taking Newton's laws as a de facto standard, that they work. And now we're using Newton's laws with confidence instead of using Newton's laws to prove the way the universe works. So note that there's a distinct difference here. We're going to accept Newton's laws as fact, that they are the way the universe operates. Don't worry, we'll do labs and show you the examples, and we'll show relationships between force and acceleration, but we're going to accept them as fact. We're not trying to prove Newton's laws. So I want you to understand that from the beginning. We're going to accept this as a framework to solve problems. We're not going to attempt to try and show you how Newton's laws are real. I'll leave the lab for that. And when I say framework, today we're concentrating on single object, multiple force. That will be your first test on force. Will be a single object multiple force test. Single object tests are relatively straightforward and allow us to focus on forces specifically. After this, we're going to do multi-object problems. And for those, we're going to deal with systems and inertia. So for right now, we're going to worry only about single object problems. I bring that up because Newton actually has 3 laws. We're only going to discuss 2 of them for the time being. And I call them the law of inertia and the law of acceleration. Meaningless names. First and second law is just fine. Now, I do this only because it's a part of pop culture. Both of these laws are a part of your probably your vocabulary already. Words like inertia have definitions in your mind. And those of you who have been physics students before understand that the word inertia has a specific definition in physics. We've already defined acceleration, so I already know that you guys have a better idea of what acceleration is about. When we say law of inertia and law of acceleration, there's a colloquial term or a colloquial phrase here that you've already heard. So let's go ahead and get that out of the way. The law of inertia, the colloquial phrase is objects in motion tend to stay in motion. That's a colloquial phrase. It's a pop culture phrase. It's not the law, and it's not the law in its entirety at all. But I'll say it again because you guys have heard it before, that objects in motion tend to stay in motion. That concept is the concept of inertia. It's not the definition, though, and it's not really what the law states. What the law states is a little more specific, and it states this, that objects will maintain their state of motion unless acted on by an outside unbalanced force. I'm not going to write all that in here. Oh yeah, I'll repeat it twice. Objects will maintain their state of motion unless acted on by an external, I use the word outside first, you can interchange those 2 words, external unbalanced force. Now, it's ridiculous that there's actually 2 laws here, because the mathematics of this law actually are relatively easy to write down. The mathematics of this law is just the net force equals 0 law. But the law has nuance, and that nuance is often lost on students. Let's look at and dissect the first part of the law. Objects will maintain their state of motion. Now, this means that the objects aren't at rest necessarily. they will maintain their state of motion. Their state of motion is velocity. So an easier way to say this is objects will maintain their velocity. The law states state of motion, but you may want to put next to it or put above it that state of motion means velocity. Objects will maintain their velocity. Even if that velocity is zero, objects will maintain their velocity, even if that velocity is zero, unless acted on by an external unbalanced force. It's important that you understand that this covers all objects at rest and all objects moving at a constant velocity. I'm careful not to use the word speed here. So all objects at rest and all objects moving at a constant velocity are covered by the first law. The reason why I'm emphasizing this is the converse of this law is also true. Okay, so meaning objects will only change their state of motion unless the forces are unbalanced. If you want to get something to change its motion, you must unbalance the forces. Find some way to do so. But it also suggests then that if you see an object in space and it's moving at a constant velocity, there's no unbalanced force acting on it. Now, that might not sound impressive or important, but we believe the cause of all changes in motion to be force. So if you see something's motion change, well, that brings up the second law. But if you see something's motion change, even if you don't know why, there must be an external force or an unbalanced force acting on the object. That's Newton's second law. It's a law of acceleration. That an object experiencing an external unbalanced force must accelerate. An object experiencing an external unbalanced force must accelerate. The amount of the acceleration depends on the object's inertia. The amount of the acceleration will depend on the object's inertia. Now today, we're just going to reference inertia as the object's mass. We're going to say that mass is the object's measure of inertia. Later on in the year, we'll expand that to cover momentum. That an object's inertia is also measured by measuring its momentum. But for right now, we're going to say that its inertia is measured by measuring its mass. An interesting aside here is that on Friday when we talked, I indicated that gravity was caused by mass, and that we weren't sure whether mass caused gravity or gravity causes mass. It was not assumed that gravitational mass and inertial mass were the same thing, and Newton didn't assume it. So his original formulations for all of physics included different references to inertial mass and gravitational mass. It has since been shown that they are the same thing, but there was no reason to believe they would have been. In the same way that charge isn't the same as mass. So we now believe that inertial mass is the same as gravitational mass. And this is why we never had to worry about the mass in doing anything when it came to kinematics. Things fell in free fall because their mass was their inertia and the reason for their gravitational force. That's why M cancels out so much in physics. It's a weird coincidence that makes physics a little bizarre. There's no reason to believe that this coincidence actually had to be this way. I think it's the reason why space gets warped, to be perfectly honest with you. I think gravity is a result of inertia, but I have no physics to back that up. All right, so that's the framework. I want to talk about how it works in practice. So Newton's law problems are always broken up into two types. First law problems and second law problems. And the first thing I would always suggest you do is determine the type of problem you're dealing with. So you'll notice that I will always ask from the beginning of a problem, do we know what type of problem it is? If you want a set of steps, that's hard for me to do when it comes to Newton's laws, at least at this point. But one of the things you should always do, you should always begin by seeing if you can answer that question. Is this going to be a first law problem or a second law problem? If it's a first law problem, you know the net forces on the system has to be equal to 0. If it's a second law problem, you know the net forces on the system has to be equal to ma. If you can determine that, that will simplify your work. If you can't determine it, like there's not enough information, you have to assume second law unless proven that it's the first law. You must assume the system accelerates unless proven otherwise. But there's all sorts of things that will tell you if it's a first law problem. The most important is look for any instance when the object has a constant velocity. If they don't tell you explicitly that there's an acceleration, look to see if the velocity is constant. If you know it to be constant, you know the net force has to be 0. Look, the coffee filters, when dropped, started out by accelerating, but they reached a constant velocity within like a few milliseconds. Your systems can transition from being second law to being first law, and it's your responsibility to know when each system is in the first law or the second law, and to use your knowledge to help solve the problem. Now, although this is the best way to start, by seeing if it's a first law or second law problem, the next thing you have to do in any situation or any circumstance is draw a free body diagram. And let me just be very, very clear. You will have to do this on the AP exam for credit. And they're going to be vicious in their application of credit. You can't have any extra forces. You can't have too few forces. If you want these points, your picture has to be spot on. Moreover, they may give you no credit just because they don't like how messy your drawing is. So be aware that when we're talking about a Newton's law free body diagram problem, you better break out the ruler. And your arrows better be proportional to the size of the force in which you're applying them. AP's ruthless. When it comes to this, they want it perfect. And although you might only have 3 or 4 points on your entire AP exam attached to your free body diagram, you do understand that these are the points that you want to get, right? Yeah. So let's talk about a simple example. And from that simple example, I'll do my best to tell you how to draw a free body diagram. And the simple example is this. I want to talk about the forces acting on an elevator to accelerate it upwards. Okay, that's our first problem. We're going to talk about an elevator. We're not talking about the person in the elevator. We're just talking about the box itself. When you're dealing with a free body diagram, the thing you need to consider is what is acting on your system. So, a free body diagram takes your system and reduces it to a point. So, free body diagram. 1, reduce each mass to a point. That seems obvious. It's not. You have to be clear about what is the mass that you're interested in looking at versus extraneous information. A picture of a person in an elevator might make you think you're dealing with the person and the elevator. But if you're only asked about the elevator, the only dot you have to draw is the one for the elevator. So just be careful and be clear that your dot represents one mass at a time. Second, I always like you to take a moment and identify any fundamental forces. Any fundamental forces affecting your problem. Now, from the onset of any problem, there are only 4 fundamental forces. And in this class, there will only be one of them that can affect your problem, and that's gravity. But identify whether gravity is actually playing a role in your problem or not. Look, 90% of the time or better, gravity is playing a role in your problem. Gravity is the weight of your object. So to identify it, you draw an arrow in the direction in which the force acts, proportional to what you believe the force's size should be, which is why I would always begin with the weight if you can. So draw an arrow in the direction of the weight. So this is going to be simply an arrow straight down. I'm careful to draw it in such a way that I could use this arrow in order to identify the size of other forces that might be acting in the system. You should also identify it with a letter, so it should be labeled. I tend to label weight with just a capital W. And just so you guys understand, this is different than your textbook. Your textbook likes to make all forces have a capital F and then a subscript for what they're supposed to be. I believe that looks pretty messy pretty fast. If you like that, go for it. It's not going to affect your answer. It won't affect your number of points available to you on the exam. I just don't like it. Yeah?
Can we also use MG?
When you're labeling forces, try not to label them. Try not to use expressions in the beginning. Because usually they don't care, but they will often say things like, don't break it into components, don't add expressions to your system. So start with the letter. We know that weight, and I say we, second period won't know this, but you guys do. The weight is the force of gravity, and it's measured by just doing mg. And we could prove where that comes from, but I don't think I have to. It just comes from dropping something. The only force acting on it is, well, gravity. So its acceleration would be g. But I would, in the time being, I would list it as just weight. Now, after you've identified fundamental forces that act in your system, the next part is to consider contact forces. Contact forces are what you already know about. These are the forces that are only applied due to contact with the object. You can see these forces. And we have special ones we're going to use. Generally, contact forces get broken down into about 4 different categories. We're going to focus on these categories specifically. The first one are pushing forces, also known as normal forces. Normal forces are so named because they are perpendicular to the surface. That's why they're called normal. They're not normal because they're ordinary. We're using the technical word from geometry as a normal. For there to be a normal force, there must be a surface in contact with your object. The elevator has no surface in contact with it. So there's no normal force acting on the elevator. There's a normal force acting on the person in the elevator, but I'm not interested in that force. Next, pulling forces. Pulling forces are going to all be classified as tension forces. They require a conduit or a connection between the object and the thing applying that force. So a cable, an arm, a handle. These are all going to be tension forces. And tension forces can be in any direction. I hate to ask who that was. Good. can see if my door's locked. Any direction away from the object. Now be aware, in general, tension forces act along the conduit, but we need to be careful about that. There are times when a tension force can be deceptive. In this case, there is a tension force. It's a pulling force from the cable. When identifying it and drawing it in, if the elevator is accelerating upward, which is what I originally stated, I want to draw this in such a way that I'm taking into account the idea that this force is greater than the weight acting downwards. Again, I indicated the elevator was accelerating upwards. So in drawing this picture, I want to draw the upwards arrow larger than the downwards arrow for weight. I want to let the grader know that I understand the only way the elevator accelerates upwards is if the tension is greater than the weight. Now, the other two categories of forces aren't involved yet. I'm not going to bring them up for a couple of days, but they are friction. That's one surface sliding against another. Friction is whenever one surface slides against another, it is always against the direction of motion. Emphasize that. That's not obvious. It feels like it's super obvious. It is not. It's always against the direction of motion. I promise we're going to see an example almost right away where the direction of tension is going to throw you for a loop. And for drag forces. That's moving through a fluid.
Did we do drag forces last year?
A little bit. This year you'll have to actually do it mathematically. Drag forces exist whenever you're moving through a fluid. Gases, liquids are all fluids, so they all apply drag. All right. So, drawing a free body diagram. It will be on the exam. It'll probably be on the multiple choice and the FRQs. Your ability to do it will be tested. When you draw a free body diagram, your diagram should be clear, concise, contain only arrows, start from a dot, and be clearly labeled with the forces. If there's more than one tension, number them. More than one weight, number them. But a free body diagram can only be made for one object at a time. If there's more than one object in your system, then either you have to treat the entire system as one object, or you have to break it up into multiple diagrams. Now, once you have your system, you should always take and carefully decide what direction will be positive and what direction will be negative. And be very clear. Our problems are almost always going to be two-dimensional. So be particular. Sometimes I'll have you go as far as to superimpose a coordinate system right on top of the dot. The reason I didn't here is you'll be asked to make a free body diagram. That free body diagram is not for you to work on. That free body diagram is for the graders to see if you know the forces acting in the system. If you need something to work on, where you have to break something into a component or deal with angles in any way, you'll need to draw a second diagram that's for solving the problem. And I will mimic this on every test, that there's what you turn into the graders as a free body diagram, and then how you solve the problem, which is separate. But once you've done all this, the actual solution to the problem isn't nearly as hard as all this part. Gee whiz. So 3 is apply Newton's law. It's going to either be that the sum of these forces equals 0, or the sum of these forces equals ma. Be aware, though, these are both vector equations. Because they're vector equations, they must be handled in one dimension at a time. If your system is two-dimensional, you will need to break this up into net force in the x, net force in the y. If it's three-dimensional, be prepared. You're going to need to break it up into 3 relationships. Newton's laws work, but they are the most complicated way to solve a problem that's possible. Once you get to this point, you are generally identifying either a force or an acceleration. The problem will dictate which. So let's do this as a sample real quick. Let's do a problem and see how it would work out. So we're going to do the elevator problem, except this time I'm going to put some numbers to it. Let's say the elevator, there you go. Say an elevator has a mass of 1,200 kilograms. What tension would cause it to accelerate at 1.2 meters per second squared upward? All right. We've done 4/5 of this problem already. Calling back to our original picture, which I can use, there are two forces acting on this system: tension and weight. Students get in trouble with what's about to happen here, so please don't. If these are the two forces acting in the system, and this is my free body diagram, when I write out that the net force equals ma, this is a vector equation. It's a set of instructions that tells me how to handle this problem. It says add up all the forces and set them equal to ma. When I do that, I need to take their direction into account at this moment, the moment when I'm adding them up. This is different than your book. So when I say take this moment to decide, if we've decided that upwards is positive and downwards is negative, I'm going to explicitly write the tension as being positive and the weight as being negative, and set that equal to ma. I do this a specific way, your book does it a different way. If you want an alternative, read the book. Now, ultimately, this is the end of the problem. We have applied Newton's law. The rest of our problem is very often algebra. In fact, we wanted the tension in the cable. The tension in the cable is going to be ma plus the weight. But this isn't sufficient. To get a numerical answer, you're going to need expressions for the weight and something to substitute in for m and a and all that kind of garbage. If your problem is looking for an expression, you might be done right here. The most common substitution you will make is that weight in this class is almost always going to be mg if we're near the surface of the earth. Please understand that that's not going to be the case all the time. A satellite, space shuttle, a rocket, a moon, they don't have a weight that's given by mg. If the moon is that close to the earth, well, we've got another problem entirely. So understand that mg is just when we're talking about stuff near the surface of our earth or any planet where we assume that the gravitational field is constant. Most of the time it won't be. So it's nice when it is, it's nice when it works out like this, but be aware that it doesn't have to be. Don't take it for granted. But in this problem, tension's going to equal ma plus mg, which means the tension in this cable is 1,200 times 1.2 meters per second squared plus 1,200 times 10.
So we keep the problem in kilograms?
Has to be in kilograms. Now you can grab your calculators and work this out, and you should. But please note that the answer for this is going to be in units of kilograms meters per second squared. So get the number, but the unit is more important to me than the number. The kilogram meters per second squared is the unit of force. which we will call the Newton. The Newton is the unit of force. And the comparable unit for force in the English Standard System is the pound. So pound is also a measure of force. We tend to not ask people what their weight is in newtons. What's funny is when they take your weight in a doctor's office, they write down kilograms, and that's not true either. That's your mass. But weight is a force. Anyways, that's the end for today.